Hello, this is Yamamoto, and this is my Physics Lab 3 presentation. For Lab 3 Part 1, we were tasked with finding the mass of a theoretical black hole using a computational model that simulates gravity between a star and the black hole. For Part 2, we were tasked with using a similar computational model to find an initial velocity for a spaceship attempting to get really close to a black hole without falling into it, leaving from a planet. To find the mass of the black hole and the initial velocity of the spaceship, glow script codes were used. The result of the lab found the mass of the black hole to be that, and the initial velocity of the spaceship to be that. For this lab, an important fundamental principle is Newton's second law of motion. It states that the force acting on an object is equal to the mass of that object multiplied by its acceleration. In this lab, the net external force equals the change in the momentum of a system divided by time. This law of motion can also be used to create the velocity update formula and the position update formula, which is important when we code. Two important physics ideas used in this lab are the universal law of gravitation and the gravitational constant. The universal law of gravitation states that an attractive force on an object due to another object is dependent on the masses of the objects, the gravitational constant, and the distance between them. The gravitational constant is a proportionality constant required when doing calculations based on this law of gravitation, and it's equal to about 6.7 times 10 to the negative 11th. Another important physics idea is the parallel and perpendicular components of net force. The parallel component is shown by p hat, which points towards the direction of the motion in the positive direction, and the perpendicular component is shown by n hat, which points towards the center of the turning circle in the positive direction. For part 1, a star, which is the system, with known mass, orbits a black hole with an unknown mass. There are no other forces acting on the system except for the gravitational force of the black hole. For the initial conditions of the computational model, we used our Georgia Tech email to create a random seed for the system, and we inputted the gravitational constant and the mass of the star. Here's the code and the important equations that were converted into code in order to form the iterations in part 1. This includes the net force, the parallel and perpendicular components of the force, and the formula to determine the mass of the black hole. This is the resulting model from the code. The code calculated the magnitude of the final net force, the magnitude of the final parallel and perpendicular component of this force, and created a calculation for the mass of the black hole at each iteration. This computational model provided 458 masses for the black hole, and the mass of the black hole became the average of those masses. For part 2 of this lab, a spaceship with known mass is released with an unknown velocity from a planet with known mass to attempt to get close to a black hole without getting sucked into it. There are no other forces acting on the spaceship except for the gravitational forces of the black hole and the planet. For the computational model for part 2, I inputted the initial conditions, showing the mass of the black hole, the gravitational constant, the mass of the planet, and the mass of the ship. To calculate the forces acting on the system, I had to add code that computed how each object was affected. The top half shows the code for the net force acting on the planet based on the law of universal gravitation formula, and then the same code was then applied to the spaceship as shown on the bottom. In order to find the initial velocity, trial and error was used until I found an initial velocity that sent the spaceship close to the black hole without getting sucked in. This was the found initial velocity, and the closest distance was also calculated. Possible sources of error. For part 1, there's a slight rounding error that occurs when calculating the mass of the black hole after each iteration, along with rounding the gravitational constant. For part 2, there's also a slight rounding error for the mass of the black hole, the gravitational constant, and the velocity values at each iteration. How are the net force and its parallel/perpendicular components different from the rate of change of the momentum and its parallel and perpendicular components? The net force with its components is actually equal to the rate of change of momentum. Its components also follow this as well, as seen by these two formulas. What if we wanted the spaceship to go into orbit? In order to put the spaceship into orbit, the new initial velocity would have to be lower in magnitude with a much more prominent y component instead of a prominent x component, as seen in part 2. Using these parameters, I used trial and error until I found an initial velocity that put the spaceship into orbit in the model, and this velocity is shown.